last time we tried to derive the Hamiltonian for coupled simple harmonic oscillator, which will account for the phonon modes in solids. And remember, we find that we need to diagonalize this big harmonic potential matrix, and after we diagonalize this matrix, we find a unitary transformation which diagonalizes big potential matrix, and that basis serves as normal mode coordinates, where we could define our momentum operator in such normal mode coordinates. And today we will go on and continue analyzing this Hamiltonian once we diagonalize this big potential matrix and find the normal mode. And we can then just combine this kinetic energy and potential energy term, where this potential term is nothing but this 1/2 kx squared that you are familiar with in, say, classical quantum mechanics. That's the harmonic potential. Okay? And YQ is the normal mode coordinates, which is the linear combinations of all these real space coordinates. And this diagonalize the matrix element of this potential term, harmonic potential term, is called VQ, where Q runs from, say, the first normal mode to all the nth normal modes, where n goes to infinity. And we can put it in the standard form of this harmonic oscillator. The only difference is that we need to sum over all the normal mode. Okay? Whereas in quantum mechanics, there's just one mode. We don't need to sum over the Q variables. And also we defined in the last lecture normal mode momentum operator, which is the same definition, which is minus IH bar partial YQ. And this is the same definition as we defined the usual momentum operator in a, say, XYZ coordinate. And of course, the commutation relations in this formalism, say, between YQ and PQ, satisfy the same commutation relations that you are familiar with in the ordinary quantum mechanics. So we will take advantage of these relations, and then we can define the phonon operator, which will be a linear combination of YQ and PQ, just like what you learned in quantum mechanics for a simple harmonic oscillator. So then we could just introduce this bosonic operator, which I call this VQ, which is the destruction operator. And we simply follow what we learned from the quantum mechanics. But this time, it's a bit more complicated because we need to sum over the normal mode. And you could show that this operator, B and B dagger, satisfy this standard commutation relations for bosons. Okay, so I leave this to you as a homework exercise to prove it. So you already knew that the Y and P satisfies the commutation relations in quantum mechanics, and if you form a linear combinations of Y and P in such a manner, and you define as B and B dagger, and these two operators, B and B dagger, also satisfies standard commutation relations. But of course, this IH bar is gone because it has been absorbed in the definition of B and B dagger. So then we could just rewrite the Hamiltonian in this new basis, and the new Hamiltonian looks extremely simple. Simply just the sum over all the normal modes in satisfaction is just a single simple harmonic oscillator energy, which is h bar omega q times this number of bosons plus 1/2, which is familiar to you. Okay, so this is the end of last lecture. So now we should use this formalism in the specific example. Okay, so a simple example of such a coupled harmonic oscillator in second quantized representation is the Fourier transform that allows you to transform your coordinates into the normal mode variables yq. And when we define such transformations, what is in our mind is this one-dimensional ring where there are some atoms arranged in such a circle. Of course, it doesn't need to be a circle, but just for the convenience, we consider such periodic structures that after you go around a complete circle, the displacement vector is back to the YL. It is called periodic boundary condition. Suppose that actually we go around this circle, and once we complete the circle, the displacement variable should go back to this YL. And we consider such rings of harmonic oscillator problem, and we could define such a matrix T which will diagonalize this potential matrix is given by this Fourier coefficient, okay, e to the minus IQL. And indeed, from this periodic boundary condition, and we know that this, say, momentum variables or wave number Q is quantized. Because the wave function should go back to this original value once you complete a circle. As a result, this Fourier, say, variables Q is actually quantized, and the value is 2 pi n divided by capital N times A, where A is the lattice distance, lattice constant. And capital N is the number of atoms, and little n is the quantized value, running from 0, 1, 2, all the way to infinity. Good. And what about the Vg or Vq? So it is the meshes element of a transformed basis. So in other words, the potential in the matrix after this unitary transformations is going to be diagonalized. And that meshes element is given by this phase difference. So this is also nothing but the Fourier transform, okay, from the real space to the normal mode basis. And they differ only by a Fourier coefficient. If you sum over all this Fourier series, you get back to this VQ or vice versa. And we also know that in this periodic system, the potential, say, matrix element of this potential term is actually translational invariant. It shows translational symmetry, meaning it is only a function of the distance between L and L prime when you calculate the matrix element of VLL prime. Okay, so it is because that the system is exactly the same if you shift your atom by a lattice constant A or integer multiple of the lattice constant A. And therefore, this potential is only a function of the distance or this difference between this vector L and L prime. So I call this capital L, and we will come back to this in just a moment. Okay, so based on this Fourier transformed matrix element, the potential term, and we could evaluate this V of Q. Okay, so let's take a short break. When we come back, we will continue evaluating this Fourier component of the potential term. So I think you can find this relevant, say, equations in our reference books, Kittel's second book, Quantum Theory of Solids, and also Flansburgh, Quantum Many Particle System. Okay, so this VQ is nothing but the Fourier sum of this VL, and you need to sum over both L and L prime, but the fact that this, inside summation, this stuff that need to be summed over depends only on the relative distance between L and L prime, but you need to sum over both L and L prime, and therefore there is just one extra dummy variables, which will be sum over. And so you need to just sum over one of them. Okay? For example, L, but the other summation L prime is just a dummy variable, so you sum over this number 1 for n, capital N times. So there's a factor of n here, which cancel that n in the denominator. And we will come back to this just a moment. So this is just sum over L, VZI, Q, L, VL. So let's just look at the harmonic potential itself. As we mentioned already last time, that in general, this is the very complicated matrix elements we consider here, because every atom is connected to every others by the spring. Okay? So once they vibrate, everyone depends on everyone else. But in general, it's not possible to study this complicated lattice vibration. We can only make progress when we treat them in an approximative way. Namely, suppose we consider just a leading order term where the interaction only involves nearest neighbor. Meaning, suppose this atom is what we try to analyze, and the lattice vibration, which will involve this atom marked by red, is only this nearest neighbor. Okay, left and right. But of course, this vibration of that red atom will affect all the others. But this kind of effect is really negligible if it is over one lattice spacing. Okay, so this is our assumption or approximation that potential term involves only nearest neighbor atoms. So with that assumption, we are able to make progress. So suppose I have a potential which takes this standard form by the Hooke's law, but then I can only consider the nearest neighbor potential term where this potential energy is is just standard form 1/2 k, which is spring constant, times this square of displacement, which is simply just a difference between these two nearest neighbor displacement. This is the simplified interaction or potential, harmonic potential, which is the nearest neighbor potential term. So now we could expand this nearest neighbor potential energy in such a form that we simply just expand the square of this difference between these two displacements on the adjacent nearest neighbor atoms. And of course, you get YL squared, YL plus A squared minus 2 times YL times YL plus A. But of course, this the summation over YL squared is the same as YL plus A squared, because you can shift this L by L minus A, and therefore this little A's got cancelled. So you got this two identical summations, and therefore I get factor of 2 here. Since this L is actually is periodic, and so I could easily shift my origin of my lattice by a lattice constant A, so that this sum over YL plus A squared is the same as YL squared summation. Okay, and therefore there's a factor of 2 here. Okay, so let's just combine everything. So this V under the assumption is given by sum over L 1/2 of K to YL squared minus 2 YL plus A. But we need to put it into the standard form, which is the summation over both L and L prime. So then we could identify this matrix element VL L prime by this identity on left-hand side, okay, of our nearest neighbor approximated form. So now let's just identify this VLL prime matrix element. You can very easily see that depending on whether L is equal to L prime or their adjacent sites, or they are just on site. Okay, so there are 3 different values that this VRL prime can take. One is the onsite, where this L is the same as L prime. So if you plug in this condition here and compare this coefficient, say in front of the YL prime, you will get this 2K. Okay, because this is the 1/2 here, 1/2 there. So when L is the same as L prime, you get 2 times YL squared, right? And therefore times K, and therefore this coefficient is 2K. So, but if they're not the same on the same side and they differ by just a lattice constant plus or minus A here between L and L prime, and you can very easily see that this is minus K. You need to actually avoid double counting, so you need to divide this factor 2 by factor 2, so you get minus K here. But if L and L prime are further apart than the nearest neighbor or on site, you get nothing, okay? Because there's no other contributions other than on site or nearest neighbor sites. Okay, so VLL prime is 0 otherwise. So let's just look at the consequence of such a simplified harmonic oscillator problem. See, that's VL, where L is defined as little l minus little l prime, which is the same as VLL prime, which is 2K. L is the same as L prime minus K nearest neighbor and 0 otherwise. And therefore we could evaluate V of Q, which is the Fourier sum. And you know that VL or VRL prime takes only 3 possible values, 2K minus K or 0, and therefore you simply just separate this summation into 2 different cases. One is when L equals to L prime, meaning capital L is 0, and this is going to be 2K plus VA, which gives you minus K times e to the I Q dot A plus VL minus A, which gives you minus K e to the I minus QA. Okay, so let me just clean up the notation. This leads to 2K times nothing minus K e to the I QA minus K e to the minus I QA, which is 4K times psi squared QA divided by 2. Okay, so I simply just use this simplified potential term, which involves only nearest neighbor atoms, and therefore the matrix element for such simplified harmonic oscillator problems is given by this general matrix elements, which takes only 3 possible values. And plugging these 3 possible values via L prime to this Fourier transform and to evaluate VQ, and VQ then is going to be proportional to the sine square QA over 2. Okay, so remember there is a relation between frequency omega q and VQ, which is the diagonalized matrix element, and you get so-called dispersion. This omega q corresponds to the frequency of these phonons. Okay, so remember this phonon energy is given by h bar omega q, just like energy of photon, right? So energy of photon is given by h times nu, which is h bar omega photon. Okay, here is the same thing. So we second quantize this simple harmonic oscillator, and we also quantize the coupled harmonic oscillator, say in 1D. And by evaluating this matrix element in the Fourier space, V of Q, and we know the phonon frequency, and therefore the phonon energy is given by h bar omega q. Okay, and that's so-called the dispersion relations of lattice vibration. Okay, so which means that this phonon energy depends on the momentum transfer. Q and in this specific form. And we could plot this phonon energy or frequency versus the Fourier variables Q or momentum of phonons. You get this kind of sine shape. So because this is the sine square, and when you take the square root of this VQ, which is square root of the sine square, so you should get the absolute value of the sine function here. Which makes sense because the phonon energy should be positive and should not be imaginary. So it takes the real value, and therefore this must be the absolute value of the sine function here, which is precisely shown here, that this is the absolute value of the sine QA over 2. So this is what we call this phonon dispersion. The interpretation of phonon dispersion is this. So you give me a value of Q as a phonon momentum, and I report you the energy of phonons. Okay, so the phonon energy depends on the momentum. Remember, this momentum transfer Q is the excitation momentum, right, which is the energy that you inject in the system to excite the system. And remember, just like what we study for this Coulomb screening effect and Thomas Fermi wavelengths, right? So you know that we always interested in this small momentum transfer limit, where the energy that inject in your system is really low. Okay, so we are always interested in this low energy excitations, where the small momentum Q representing the momentum transfer to your system is really, really small. Okay, in that limit, you really can talk about the low energy excitation, because the low energy refers to this low momentum transfer or low external energy that you put in your system, and which corresponds to the low temperature limit of the system. Okay, so if the temperature is low, then most likely the system is just in that region where Q is really small. At low temperatures, you cannot expect that this Q becomes very large, and Q should be small. And this is the interest of a study, that when Q is really, really small, and you can see that the sine function is actually approximately given by a linear behavior. Suppose this is x, which is defined as Q over 2, then the sine x is approximately given by x if x is really, really small. Okay, and this is so-called the linear dispersion relation that oftentimes we are interested in when we study the low temperature phonon, right? So this is linear dispersion, meaning the relation between h bar omega q and q is linear, and the prefactor is simply just given by this 4 times k. No, this is 2 times square root of k over m, and times this little a divided by 2, so whatever. So this is just telling you that this prefactor depends on this spring constant that you assume in the very beginning. Of course, this uniform spring constant is just an assumption here. So this is just assumption that all these atoms are affected in the same way, where there's all the springs attached to the neighboring atoms is of the same strength, meaning all this, the spring constants k all the way to the very end. Of course, this is a very ideal situation, but it turns out that this approximation is a reasonable one, because in reality, we'll show later that indeed this linear dispersion for some phonons is really the case here. And once we've done this and we know everything, and we could calculate all the thermodynamics at low temperatures by taking this linear dispersion of the phonon. And we will come back to this in just a moment. So this is just a simple example of phonons in 1 dimension. Of course, we are dealing with the phonon in 3 dimensions, but we could straightforwardly generalize this 1-dimensional phonon calculation to 2D and also to 3D, more realistic phonons. Everything okay? Good. This is just a harmonic oscillator, and then you sum over all normal modes, and then you could simplify this problem by considering just a uniform Hooke's constant, okay? And then consider nearest neighbor interactions, and then boom, you get the answer, which looks very realistic and reasonable. Great. Of course, you may think that if you increase the temperature, and then this dispersion is not a straight line, but it bends over, right? So that's the high temperature regime. And we will worry about this later, but not here. Okay, so since we are more interested in the low temperature limit of this phonon vibrations. All right? Okay, good. So if no other questions, we will continue to generalize this calculation to 3-dimensional phonon. Okay, so let's take a very short break. So by the way, you could read the corresponding section chapters in all the references, such as Kittel's second book and also Fransberg. Okay, so now let's just generalize this lattice to 3 dimensions. Of course, this is not easy to draw on a blackboard, so I just use a 2-dimensional lattice as a simplified version of the 3D lattices. And the general lattice vector, L, is given by the linear combinations of the 3 lattice vectors, right? L1, L2, and L3, which are unit vectors corresponding to the lattice vector. You can also define the reciprocal lattice vector, G, such that e to the I G dot L is 1 for all L. And you sum over L e to the I G dot L is 0 unless Q is same as G. Okay, so in other words, this reciprocal lattice vector is actually the so-called inverse of your lattice vector. And so now let's just write down the Hamiltonians, which is nothing but the 3D generalization of the 1-dimensional phonons. Except now this summation is more complicated. V L prime J. We just expand up to this harmonic or second order imperturbation. So remember now, instead of just a single direction YL, you get 3 different kinds of displacement vector. Remember, the atoms live in the 3-dimensional world, so you could define your displacements along 3 different directions in 3D lattice. So now this is YLX, so YLZ, YLY. And so I use I and J represents to represent such displacements along different X, Y, and Z directions. So you need to sum over all possible quadratic terms of displacement, say different side L and L prime, also along different directions. Okay, it's a really complicated summations, but at the end of the day, it becomes controllable if we are able to diagonalize this very big matrix, in terms of 2 consecutive diagonalizations. So let me just use harmonic approximations, and in particular, I can use a matrix, a column and row matrix, to represent such horrible matrix elements. L prime, XX, V, L prime, IJ, and V, L prime, JI. So it's actually a 3M by 3M matrix, right? Okay, so it is a 3 by 3 matrix if you fix this L and L prime. Okay, but both and L prime can run from, say, 1 to n, right? And therefore, each of these matrix elements is actually representing n by n matrix. So it is a 3n by 3n. Okay, good. So let's just call it a day today. And on Wednesday, we will start from the 3n by 3n matrix and try to diagonalize this very big matrix in 2 different steps. And then we will, again, try to find this normal mode along all these different directions, and we sum over all the normal modes. Just becoming a really messy but durable problem. Okay, so I'll see you on Wednesday.